Welcome to week 2. And this week, we're going to be looking at first-order equations again, but specifically at linear differential equations. We're going to learn how to solve those, and we're also going to see how they appear in modeling problems. Linear is the new term that we're going to be considering, so let's focus on that. A linear first-order equation is one that can be expressed in this form. And what I want to draw your attention to are the locations of the y's. So y equals a function of x is what we're looking for here. But the differential equation appears with y's and y primes only multiplied by functions of x, and maybe some stuff on the right-hand side. But the key thing is here that there's no y squareds, no y times y prime. Those kinds of nonlinear combinations of the y and its derivative are not allowed. What would be okay, and we'll see some examples later, would be something like x cubed y prime plus e to the x y equals sine of x. That is a linear differential equation. It's linear in the y's and the y primes. It's perfectly all right to have nonlinear x things. It's a function that we're interested in solving for that has to be or has to appear in linear form. One convenient feature of linear equations is that we can always rewrite them in a standard form. And this is the y prime by itself with a coefficient of 1. And we also include the y on the left-hand side, and whatever's left over gets put into the right-hand side. Now it is also possible, and we've seen this already, that the equation could be separable and linear. It's possible to be both. So let's take a look at this example here. This is linear because we have the y prime by itself, the y with a multiplier, that's fine, and it's in standard form. Turns out that's not going to help us write yet, but it's a good thing to keep an eye on because the coefficient of y prime is equal to 1, and all the y's are on the left-hand side, with the remainder, any other terms remaining on the right. And once we have this, and we're asked to solve, again, our goal is to solve for y equals, then, well, the only technique we have so far, we're going to increase this shortly, but the only technique we have so far is to separate and integrate. And if we're going to do that, well, this standard form actually isn't so great, because what we need is dy dt by itself so I can bring the dt up. And that means we would have to bring this 2y over to the other side. Now, once we've done that first step, now we can bring the 3 minus 2y down, the dt up, and we get 1 over 3 minus 2y dy's is equal to dt. We've separated successfully, now we can integrate. The right-hand side is the easy one. We get t plus a constant. The left-hand side, we get a ln because it's only a y to the power 1. And we'll have 3 minus 2y. And the only gotcha in here is this negative 2 coefficient. If we're going to differentiate this and get back to 1 over 3 minus 2y, we have to remember that a negative 2 would pop out. We want to cancel that in advance, and so we end up with this as the integral of the left-hand side. Then our goal is to solve for y equals, and in solving for that, we end up with ln 3 minus 2y, bring the negative 2 up. And just remember, c is just some constant. We don't know what it is, but now it's negative 2 times as large. And then we're going to exponentiate, put an e as a base underneath both sides. And on the left-hand side, we have the absolute values of 3 minus 2y's. On the right-hand side, we can rewrite this as the product of two exponentials, e to the negative 2t and e to the negative 2c. We then apply our usual trick to get around this constant and this absolute value. we're going to define a new variable, a, which will be plus or minus e to the negative 2c's. That lets us take away these absolute values and make this negative if it needs to be negative. And we end up with 3 minus 2y equals a e to the minus 2t. This part here becomes our a. This is what we're left with. And at the end of the day, we can solve for y, and we bring this over. We'd have 3 minus a e to the minus 2t, all of that divided by 2. And that would be our solution. We had a differential equation, first order. We were able to separate and integrate and eventually solve for y. Now here's the catch. It turns out that we can't separate everything. In fact, we've seen some examples where separation isn't possible. However, there is an alternative that works with linear first order. Not all separable are linear, but if it is linear, we can do the separation. What we're going to do is take our initial equation. Let's go back a step and see what that looked like again. We're going to take it in standard form, and what we're going to do is multiply through by some magic term. We're going to give it a classier name than that. We're going to call it an integrating factor. And then we're going to ask ourselves, okay, if we multiply through here, what could we multiply by so that this whole left-hand side becomes the result of a product rule derivative? This is not obvious at first glance that this will be helpful, but you'll see the pattern once you work through a couple of examples. The idea is, looking at this left-hand side carefully, we see y and y prime. And if you think of the product rule, remember the product rule states that if we take the derivative with respect to t here of, call it f times g, then let's call this y to make it more obvious. We would have f prime y plus f y prime, or let's rewrite it in the form it looks like up here, f y prime plus f prime y. And you notice we have a y here and a y here. Y prime here, y prime here. So if we can get our multiplier chosen so that m, and in this case here 2m, match f and f prime, we're going to be able to rewrite the left-hand side in a very nice, tidy way.